Hi, my name is Erica Byerley. I'm in the Applied Geospatial Sciences program at Northern Arizona University, and I'll be talking about remote sensing and GIS for debris flow hazard modeling. Debris flows are like a cross between a landslide and a flash flood. They're highly turbid flows that can sometimes partially float boulders, vehicles, or even houses. In Southern California, they present an extreme danger to residents. In all these photos, you can see debris from the Montecito debris flows of January 9th, 2018, which killed 23 people and destroyed 130 houses. From my research, I have found that improving GIS modeling capabilities at the local level could help mitigate this risk. There are several scientific factors influencing debris flow hazard. Steep mountains, chaparral vegetation, wildfire, and storms with high rainfall intensity are the most important variables leading to debris flow initiation. In both of these images, you can see how steep the San Gabriel Mountains are. On the left, that's the skyline of the city of Los Angeles for reference. And chaparral vegetation, when it burns, it tends to leave a hydrophobic layer on the surface of the soil, and that's from the waxy substances in its leaves burning. And so this hydrophobic soil layer will increase runoff from any storm, which is likely to lead to a debris flow. Several human factors also influence debris flow hazard. With the large populations of Southern California, there's been a high degree of engineering the urban wildland interface to provide more human habitat areas. This is Trancas Canyon in Malibu, and you can see two debris basins that have been constructed to attempt to protect residents of this neighborhood from debris flows, along with a channelized stretch of Trancas Creek, which still has a little mud in it from debris flows that occurred a couple days before this image was captured. Although in this instance, these engineered structures were sufficient at protecting these residents, there have been many instances of engineered structures failing and people being buried alive in their beds by debris flows. Interagency coordination, communication with the public, and emergency response are also extremely important for mitigating the danger of debris flows. For my research, I analyzed watersheds that had debris flows in several study fires throughout Southern California. So I compared watersheds with debris flows to those without debris flows and analyzed variables that might influence that. I looked at the study fire, Woolsey fire, station fire, and Holy fire. So to do this, I first needed to delineate watersheds in each of the burn areas. I followed this work sequence. The hydrology toolkit in ArcGIS Pro provides the tools you need to complete this. I also created several remote sensing indices from satellite imagery for each fire. NDVI is a vegetation index. NDSI is a soil index that characterizes soil brightness. BSI is the bare soil index, and DNBR is a burn severity index. This is the complete list of variables that I analyzed with ordinary least squares regression. The values for each of these needed to be recorded in the watershed attribute table, and I used several Python codes to do this. This is the mean DNBR code. So this code calculates the DNBR in each watershed and writes that value into the watershed attribute table. From this analysis, I found that the USGS Western Preliminary Hazard Model largely uses variables that are appropriate in Southern California. This is the best model that we currently have. And one thing that I found significant was that the whole soil K factor was was a more significant variable than the fine fragments K factor. This is a soil erodibility factor. I also found that the mean NDSI could be useful if incorporated into a hazard model. It was consistently significant throughout several wildfires. And I found that remotely sensed burn severity data can be useful when field verified data is not available. However, field verified data is preferred if it is timely to collect this data before a potential storm comes in. One thing that I do recommend is that local GIS analysts in Southern California run the USGS Western Preliminary Hazard Model themselves, but it would be best if they use forecasted precipitation data rather than rainfall intensity of a design storm. Using the Python codes I wrote, they will largely be able to run this model on their own. And using forecasted precipitation data will likely increase the accuracy of predictions, as well as the timeliness of the model. This work could be applied to Grand Canyon. Debris flows occur in Grand Canyon regularly, but are infrequently studied. The USGS Western Preliminary Hazard Model is unlikely to work very well in Grand Canyon. Precipitation from monsoons is highly variable. Wildfire tends to burn in flatter areas up on the rims rather than in the steep sections of the canyon that would be required by the USGS model. And the runoff interacts with several different geologic types, so it'd be very difficult to determine the K factor in this environment. But river recreators could really use this information in terms of which watersheds and which side canyons are likely to face increased risk of debris flows. They often hike in slot canyons during monsoon season. They may camp on debris fans, and they have to navigate all rapids in the Colorado River that could potentially change from debris flows. Debris flows cause the majority of rapids in Grand Canyon, and the Colorado River would normally rework these debris fans during seasonal floods, but Glen Canyon Dam currently regulates flow, and there are not currently large seasonal floods that could rework these debris fans. So rapids are likely to become worse and more difficult to navigate in this environment. The Thumb Fire, which burned in 2020, potentially puts Matcat-Amoeba and Olo canyons at a heightened risk of flash floods and debris flows during the 2021 monsoon season. However, more remote sensing work needs to be done, and a Grand Canyon model needs to be created. Any questions?